Welcome. Let's take a look at defining what is known as the differential. So to start, we need to define or let y equal f of x be a differentiable in an open interval containing x, meaning that the derivative of y equals f of x is defined in that interval. Then the differential of x, which we denote by dx, is an independent variable that can be assigned to any real non-zero number and is defined by the dependent variable dy. Now the dependent variable here is dy, and dy is defined as being the product of the derivative of f of x and the dx, the differential of x. So note that dy is a function of both x, we see that in this f prime of x, and dx. Now recall that the linearization of a function is equal to f prime of a times the quantity x minus a plus f of a. And this is the linearization where L of x is anchored or built at x equals a. Which means that if dx is small, then f of a plus dx equals L of a plus dx. So what that means is, since the linearization is built at x equals a, if I only move a small distance away from a, the linearization will produce the same y value as the original function. Again, that only happens if dx is small. Again, that means that if dx is small, then the function value of a plus that small dx is approximately equal to that produced by our linearization. So if we wished to investigate the change in the output values of f of x due to a small increase in x, we could consider the following. Now, something to note, this due to a small increase in x, we would represent as a plus dx, because recall that dx is a small value. So we would have f of a plus dx, so a plus some small increment of x minus f of a. So looking at the difference between the function values between a plus a small value and a. Now we can say that f of a plus dx is approximately equal to L of a plus dx, using this information here, minus f of a. Well, L of a plus dx is defined as using this linearization. Notice that we have f prime of a, and in place of our x, we are inserting a plus dx because we're interested in what's happening when we increment a small amount, so a plus dx minus a plus f of a. So all of this here corresponds to L at a plus dx minus f of a. Well, when we simplify all of this, what we end up with is simply f prime of a times dx. Because we see we have an a minus an a, and those will sum to 0, and we've got an f of a minus an f of a, and those will sum to 0. So all that we're left with is this f prime of a times dx. So what we really want to notice here is that we have a small change in y values. So this is a change in y values due to a change in x values. So we have a small change in y values due to a small change in x values is approximately, so we do need to pay attention. This is not exactly equal. It's an approximation. Is approximately equal to f prime at a dx. So the true change in the output values of f of x due to a small change in the input values from x equals a to x equals a plus dx is written this way. Delta y equals f at a plus dx minus f of a. Now, on some occasions, finding the difference may be difficult. So it may be difficult to find the difference between f of a plus dx and f of a. Or it could be time consuming, and therefore we can approximate delta y as delta y equals, we have the difference f of a plus dx minus f of a, which is approximately equal to the linearization a at a plus dx minus f of a, which we just saw was equal to f prime at a dx. So in essence, we can say that delta y is approximately equal to f prime at a dx. So that was a lot of words and symbols, and let's take a look at a visualization to try and make sense of what's going on here. So here we have a function f of x, y equals f of x in blue. And we've built the tangent line to this function at a, so at this point a f of a, and we can see that tangent line illustrated here in red. And now recall that we built this tangent line at x equals a, and what we're going to do is we're going to increase incrementally a. So a plus dx. So a plus some value moves us along the x-axis to a new point. Now what we're interested in is the change between the function value at that new point and the original function value. So that's illustrated here with this line. We're interested in that difference, or the true change in y that is equal to the new function value minus the original function value. Well, like was mentioned, sometimes that can be difficult or very time-consuming to determine. So what we can do instead of finding that difference is we can use our linearization to help us estimate that difference. So our linearization estimation is built on the same idea, similar idea. That is, we're going to increment a by some value dx, but we're going to use the tangent line instead. And so when we increment our value a by some value dx, we're moving along the x-axis, and then we're going to find that corresponding point on our tangent line, and then find the difference between that y value and our original y value. Now, as was noted, that often using this linear approach, this tangent line approach, which is basically the change in y is equal to the derivative of the original function at a times dx. And remember, dx is how much we're incrementing our x. That this can be a more efficient approach. And then notice that In doing this, we do have some kind of error. That error is pictured here in this pink that I just drew. Now, this error depends on how much I increment a. For example, if my dx was not nearly as large as what I have here, it was this large to help illustrate, but maybe my dx, maybe a plus dx ends up being somewhere around here. And if that ends up being my a plus dx, then if I follow this up, notice that my error ends up being much, much smaller. So if my steps, if my dx, if my increment is small, the error in using dy equals f prime of a dx is small. So let's take a look at an example. We're going to look at an example where finding delta y and dy is not particularly difficult as a means of comparison. So what we're asked is to let y equal x squared minus 2x, and we want to find both delta y and dy when x is equal to 3 and dx is equal to 0.1. And down below here we have our definitions of delta y and our linear approximation. And so let's go ahead and take a look at delta y first. So delta y is going to be y at 3 plus 0.1 minus y at 3. So this is equal to 3.01 squared minus 2 times 3.01. So that is our y at 3 plus 0.1 minus 3 squared minus 2 times 3. That's our y at 3. And so if we multiply things out, we get that this is 3.41 minus 3, which gives us 0.41. So our delta y is 41/100ths. And in this particular example, that wasn't terribly difficult to compute. Dy, on the other hand, is equal to f prime at a dx. Now, to find this, then I need to know what f prime. Now, f is our function here that defines y. So f prime of x is equal to 2x minus 2. F prime at a, or f prime at 3, is 2 times 3 minus 2, which is 6 minus 2, or 4. So our dy is 4, that's our f prime of a, and we were told our dx is 0.1. So our dy is equal to 4 times 0.1, or 1/10, and we get 0.4, or 4/10. Now, what I want you to notice is that delta y and dy are close. They only differ in the hundredths place. They differ in the hundredths place. So while this was not an example of when you might use dy over delta y, this provides us some insight into how this differential can be used as a means for approximating that true change in the y value. I hope you find this helpful.